Professor Clements with you as we discuss refraction of light. So we're going to take a ray of yellow light, just some middle of the visible spectrum light. It's starting in air. Index of refraction 1.00. The index of refraction is a measure of the speed of light in the medium. Air is not exactly 1.00, but it's close enough. In our calculations, we'll use 1.00. So if the index of refraction is a 1, if n is a 1, tell me what the speed of the light in air is compared to the speed of light in a vacuum, the c. And you should say the same. They're not exactly the same, but they're close enough for our purposes. It's more digits down the road where it's not 0. So we're going to use index refraction of 1 for air. And we're taking this into normal glass. And let's suppose that the index refraction of the glass is 1.52. 1.52 here. What does that tell you about the speed of light in glass compared to the speed of light in a vacuum? We're forgetting 1.52 here. That means our speed in the glass, the v, is smaller than the speed of light. And if I would just cross multiply here, if I put v here and put the n in the denominator, c 3 times 10 to the 8th, n 1.52, if I just round it to 1.5, then we would see that the speed of light in the glass is about 2 times 10 to the 8th meters per second. Use your calculator if you want. But as the speed decreases in the medium, the index of refraction gets greater. The index of refraction is inversely proportional to the speed of light in the medium. So as v gets smaller and smaller and smaller, the value of n gets larger and larger and larger. Okay, back to this problem. The ray is coming in at an angle of 30 degrees. We want to calculate the angle of the ray in the glass, and then I want to draw it in here. Well, this is a situation of refraction, where the light is going from one medium in certain index of refraction to an index of refraction that's different in the second medium. In these situations, we apply Snell's law. Index of refraction in the first medium multiplied by the sine of the angle in the first medium equals index of refraction in the second medium multiplied by the sine of the angle in the second medium. And we have the numbers to plug in here. Since we're working on air as medium 1, and glass, well, that be medium 2, and it doesn't matter which is 1 or 2. But traditionally, where the ray starts, that's medium 1. So 1.00 for n, sine of 30 degrees, 1.52 for the index of refraction of glass, and we're going to find theta 2. So your first step, multiply 1, use your calculator to find sine of 30 degrees. Hopefully you get 0.5. You'll be in degree mode. Watch that you're not in radian mode. So 1 times sine of 30 degrees, then divide by 1.52. You ought to perhaps pause and see what result you get on your calculator. I came up with 0.3289, keeping some extra digits here so I don't introduce round off error. And then I have sine of theta 2. So my unknown is under the control of the sine function. How can I get rid of this influence? Well, I need to apply inverse sine to both sides. So inverse sine of 0.3289 equals inverse sine of the sine of theta 2. The sine and the inverse sine are inverse functions of each other. They cancel, and I just get theta 2 on the right side. Using my calculator, evaluating inverse sine of 0.3289, again, feel free to pause and verify this on your own calculator. 19.2 degrees. So I need a ray inside the glass drawn at 19.2 degrees. And this is a reasonable result. We always try to think if it's reasonable or not. The glass is a denser optical medium. Index of refraction is higher. In those situations, the theta needs to be smaller. Now, you can think of it this way. You've got 1 times sine of 30, that's 0.5, equals this number times this number. as n gets bigger and bigger and bigger, theta has to get smaller and smaller and smaller to keep the equality. So as we go into a denser index refraction, the angle gets smaller. We get closer to the normal. The ray is closer to the normal. So I put my protractor on here and get it lined up with the edge of the glass. And then here is 0 degrees, the normal, 10, 20. I'm going to make a mark here, and I'm not going to draw the ray outside the glass. I'll just use that as a reference point. So there's the ray as it's going through the glass. Perhaps not the best drawing, but if I label it, maybe that will help. 19.2 degrees away from the normal, smaller than the 30-degree angle. So there we have the angle of the ray in the glass. Using Snell's law, index refraction multiplied by the sine of the angle in that medium, that's one side, and then our second medium, index refraction, sine of the angle in that medium. This particular problem, we ended up having to take inverse sine. If you would have been given theta 2 and n2 as the unknown, that you wouldn't have that problem. You'd have n1 sine theta 1 divided by sine of theta 2, and you could calculate the index refraction of the glass. Okay, second part of the problem. So the ray keeps on going. What's the angle of the ray as it exits the glass and moves through air on the other side? Well, again here we would draw a normal. I'll try to do this semi-accurately. What is the angle of the ray now hitting the boundary between the glass and the air? What's this angle? We have two parallel lines. We have a straight line cutting through. The theorem of geometry, probably a theorem. 19.2 degrees here, same here, 19.2 degrees. Two parallel lines cut by a straight line. These angles are equal. So 19.2 degrees. So in my calculation now, I'm in the glass to start with, so I'm again using n1 sine theta 1 equals n2 sine theta 2. And my first medium is inside the glass, so I'm going to go ahead and pick up 1.52 for the index refraction of the glass. Sine of 19.2 degrees. In air, the index refraction is 0, and we want to know what's the angle out in the air. Again, you should pause, use your calculator, and see what number you arrive at. I arrived at 0.4999 equals the sine of theta 2. Again, we're in a situation where our unknown is under the control of the sine function. To cancel this off, I need to take inverse sine of both sides. So inverse sine, 0.4999. And a little shortcut here, already done it above. If I take inverse sine of sine, those two functions cancel each other, and we just get theta 2. And with a little rounding, you get 30 degrees for theta 2. And I'll draw it here. Coming out at 30 degrees, and place my protractor in position. 0, 10, 20, 30. And my angle is from the normal to the ray, 30 degrees. And take a look at the incoming ray and the outgoing ray. They're both at 30 degrees. It's just been shifted a little bit. If I would put the straight edge on the original ray, kind of line it up there, it's parallel to the ray on the bottom side of the glass, but it's been shifted a little bit. So that's the effect of going through a rectangular plate. The angle in air on both sides is the same. We see a small angle to the normal inside the glass. So keep practicing with that. Ask your instructor questions.